Well, okay, let's get started. Exam week, yeah. Everyone is stressed out and busy. Well, now we are U of T, right? I mean, you are used to stress. You know, you're the best in this country. So, and just want to continue to finish this train of thought before we go to the midterm and move on. Last time we were talking about, first of all, the k-means. Given a set of data, how do you group them into separate groups? Yeah, and then we say, well, the k-means, the grouping is too harsh, right? You have the hard boundary. But then, so we introduce the Parson window, where you have a Gaussian kernel for each data point. You add up all of the Gaussian kernels, you get a density function that you can estimate. That's your estimated density function. But then we say that the problem there is that you have to add up a Gaussian kernel for every single data point. And when you have many, many data points, you have to add up many things. And that's difficult. And then we change gear into this Gaussian mixture model, where we divide, we say that, well, maybe the data points that we have can be grouped into different groups. And then each group is generated from the same Gaussian distribution, the same Gaussian density function, right? And it looks like this, yeah? So to generate a data point, you have to first randomly pick a group, yeah, a bump, a density function that we represent by this W, this probability. And then once you pick that bump, then you just use that Gaussian density, which is the N, the normal distribution, right? The N of mu j and then sigma j in order to generate the data point X. Yeah? And algebraically, this basically is represented in this form, right? This density function now becomes a weighted sum of the conditional densities. Yeah, this condition, each one of the conditional densities would be the Gaussian bumps, and then Wj is the probability of picking that particular Gaussian bump. So this is the Gaussian mixture model for data generation. So this is our hypothesis for how these data points that we're given are generated. Yeah, the question is, what should we use for this W and mu j and sigma j, these parameters, right? And therefore, that becomes a problem of estimating these parameters, yeah, given the data points that we have, these n data points. How do we find the best Gaussian mixture model? And what do we mean best? Would best fit to the data point that we're given. Yeah, that's where we were at from last week. Okay? And we say, well, if we describe this best fit as the log loss function, or the maximum likelihood of seeing the observed D, then we can, yeah, for example, we can try to use gradient descent, right? Or stochastic gradient descent. All of this is from our last time. I'm just copy and paste from last time, so you don't have to copy it. And so if you do, but then to do SGD, it's rather complicated, and it's very computationally intensive. So in general, we do not use SGD to solve these kind of problems. We use the new algorithm called the expectation maximization algorithm. The EM algorithm. And in fact, we have already seen a version of the EM algorithm, which is the k-means. The k-means is just a special form of EM. Okay? And so this EM will be very similar to what we have seen already. Okay? So we're not going to have a lot of work today in that sense. So again, it is a alternating optimization approach. Yeah. So we decide first, we decide the clusters, the so-called bump memberships, and then we decide on the parameters for each bump. Yeah. Okay, each bump being the Gaussian PDF. Okay. So it is n alternating optimization approach. Again, with two subproblems. Yeah. So problem one is that given the bump membership, we decide the parameters of each bump. Yeah. So suppose for each data point, that's in D, oops, sorry. We know its bump membership. In that case, then we can define just, say, B of j, right, which is a subset of the data set, which is the all set of points that belongs to that bump j, yeah? Oops. Let this denote, let's say, the set of points sampled from this bump, so say nx, the j's bump, yeah, so which is mu j, sigma j, like that, right? Yeah. Suppose you already know that, we can collect all of the points that are sampled from that particular bump. Okay. So we just need to estimate the parameters, yeah, wj, the probability of choosing the bump, mu j, the mean of the bump, and then sigma j, which is the covariance matrix for the bump, yeah? So for all of this, j equal to 1 to k, yeah? Right, these are the parameters for our Gaussian mixture model, basically, okay? So how one might do this, right? So let's say we first define mj as the number of points inside bump j. So therefore, this is just simply the size of bj, right? Yeah? Size of bj. Let's define it that way, by definition. Okay? mj. Yeah? How would you think would be a good way? What would be a good way to estimate wj? Wj being the probability that a data point is sampled from that particular bump. What would be an intuitive way? Yeah, that's right. Just the ratio, right? What portion of the points come from the j's bump? Yeah. So therefore, it seems reasonable to simply use this one, this ratio, to estimate wj. Okay. It's quite a reasonable thing to do. And how about this mu j? Mu j is supposed to be the mean vector for our Gaussian vector, right? Mean vector for this Gaussian distribution. How do we estimate a mean vector? This is the mean vector of the points inside the Gaussian bump, right? This is the mean value of the Gaussian bump. Yeah, just take the average, right? To estimate this mean value, whatever points we have, take the average. We have mj points, so 1 over mj, and then the rest will be summing up all of the xn's that's inside this j's bump, all of the values, right? That's just a so-called sample mean. Yeah, it's usually it's a good estimation for the true mean value of a random distribution. Yes? Yes.
Generally, in these types of problems, how amenable is using something like linear programming to solve them? Or how much do they sort of link themselves to be solved sort of by linear programming solvers?
Yeah, why not? If you need to. In this case, we don't have to because there are easier solutions than using linear programming. Yeah, sometimes we have to. For example, in fact, I'm going to explain that this, to show that this one is actually optimal in some sense, you have to solve not a linear programming problem, but rather a more complicated convex programming problem. Yeah. We'll talk about it. For now, let's just talk about intuition. Yeah? What is the intuitive way to estimate these parameters? How about this covariance matrix? Well, again, same idea, right? You want to estimate the covariance. You just take the sampled covariance. Yeah? Sample covariance will be, again, 1 over mj, and then summing out over all possible points inside of this particular bump, and then the covariance. So this minus mu j multiplying nxm minus mu j transpose. Remember, this is a column vector, and then this is a row vector, right? Column vector multiplying row vector, you get a matrix. Yeah? So the definition of covariance matrix would be the expectation of this matrix, right? We don't know this expectation, yeah? This sigma j, right? We don't know, so we just do this averaging to estimate it, right? Yeah? So it makes sense that we use this formula for estimating sigma j, right? It's at least intuitively makes sense. So let's call this equation star, and then this 2, let's call this is double star. Okay? Yeah? Yes?
For sigma j, is it the average of all variances that we're calculating?
Covariances. Covariance.
But I thought covariance would usually include two, like different.
Yeah. We are talking. These are the covariances of the elements inside this vector, right? This vector itself has multiple elements, right? D-dimensional vector. Remember? So D-dimensional vector is a D jointly Gaussian random variables.
Oh, yeah, makes sense.
Yeah, D of them. Okay, good. So then we're done in this step, right? This is how we're going to estimate these parameters we do this for every single j, yeah? With every single bump j, we're going to do this, and we're all done, yeah? The only question is, well, these are all kind of hand-waving intuitive thing that we should do, but is there any way for us to show that this is actually optimal in some sense? Yeah? So that's something to note. But this is a bit deeper, so I will leave this as optional, okay? You don't have to know this. I just want to, for those of you who are curious about this, and since you showed up today, I assume that you're doing very well with your other exams and so on. You are strong students, so let's talk about some of this optional stuff, just for fun. Now, the first point is that turns out that this way, that the single star, this way of estimating Wj maximizes the likelihood of seeing those Mj, okay? The N1, N2 to Nk, okay? This one, let's say, maximizes the likelihood of observing this N1 to Nk, which is the number of points in the bumps, right? The number of points in the different bumps. How do we know that? Yeah. So, well, if we have to maximize the probability, yeah, suppose we're given, well, what is the probability of seeing this N1 to Nk? Okay, that's the question. Well, the probability of seeing N1 in the first bump, N2 points in the second bump, together, kind of, almost, probably seeing all of them, kind of, but then there are many possible ways to arrange those points such that this many of them fall into the first bin, second of them fall into that bin, and so on, okay? So there is a slightly more complicated formula for that. What you're thinking is correct, but there's a factor. Exactly, some kind of factorial, right? So this is, again, each one of these bins, each one of these bumps has a probability of Wi to be inside the bin, right? Every point has the probability of Wi to be inside the bin. Now we're given n points. We just throw them into these bins at random based on that probability, right? Probability Wi. Yeah, there are so many ways to do it. And each one, what is the probability? Okay? So this is called the multinomial probability law. Have you heard of the multinomial probability law in probability course? That's 302 maybe. If not, then at least you have heard of the binomial probability law, right? Binomial is the one you have two cases only, when k equals 2. Yeah? Heads or tails when you flip a coin, well, a biased coin, yeah, with probability p, right? Just as a reminder, the binomial distribution says that the probability of having a k points, yeah, because, well, I should not use k now, L points out of n is equal to n choose L times p to the L power 1 minus p, n minus L, right? Yeah, remember this formula? So this is, what is the probability of having L points in the first spin, yeah, or toss a coin? What is the probability you see, you toss a coin n times, what is the probability that L times it shows up heads? Yeah, that's the probability. It looks like this. And the reason is that, well, this is the probability of showing heads. 1 minus p, the probability of seeing tails, yeah? If L times heads, then n minus L times will be tails, yeah? But then you have to calculate, you also have to account for how many ways for you to arrange these n tosses to have exactly L heads, yeah? So it's n choose L, yeah? But what n choose L looks like? N factorial times L factorial, n minus L factorial, right? Because now you're dividing these n points into two parts, right? Heads or tails, yeah? Heads, tails, yeah? Heads and tails, like that. Okay? Altogether, there are this many ways to find, to divide into two bins, L and n minus L, okay? This should be reviewed to you, at least, in all of the ECE 302 classes, we cover this one, because it's a basic probability law, right? But now we have to extend this to n different bins, yeah? Now a coin has more than two sides. It's a k-phase dice, let's say, yeah? You roll these dice, okay? So turns out that the probability of seeing that many n1 of them in the first phase, first bin, n2 in the second bin, and so on, is given by this formula. N factorial, you have n points again, right? And then n1 factorial times n2 factorial, these are all products, and then times nk factorial. And then here is w1, because the probability that you're in bin 1, right? Raised to n1 power, because that's how many points fall in there, yeah? And then you have wk, nk, like that, right? Yeah? So you can see, you compare these two, this so-called multinomial distribution is just a extension, very clear extension of the binomial distribution you've already seen. Yeah? Just that we have a general k rather than just 2. Okay? So if this is the probability of seeing what we see now, you know, having all those points in these different bumps, then we have to optimize, we want to maximize this p, right? We want to, let's see. We want to maximize this probability over the WJs, right? Yeah. It turns out that this is a convex programming problem. If you look at this, you know, put in there. If not, then actually you can take a log of that. You get a sum of logs, they're all convex. And you can solve this convex problem by using a Lagrange method. Well, the reason we're using the Lagrange method because we need this WJ sum to 1. We have a constraint here. So you can 1 to k equal to 1. And then WJ is greater than equal to 0. Yeah, right? We have this. These are the constraints, right? It's subject to, let's say. Yeah? So it turns out that you can use the Lagrange method to solve it. Again, we don't need to know what it is at this point. Yeah? And you solve this, you get the WJ, the optimal one, indeed is nj over n for all j. Yeah, and that checks out that theoretically what we're doing is actually good. We're maximizing what we're observing. Yeah. Again, this is upstream node, right? Just for your information. And then we also ask, well, how about the other parts? You know, the part when we estimate these guys, the means and the covariances. Okay, so exactly what we are doing when we use these formulas to estimate mu j. Turns out that this double star two equations, it minimizes the E in of omega that we want to minimize. Remember that our in-sample error that we discussed last time, right? It's just the log loss function, right? Of observing D. Yeah, we minimize this one given the bump membership, which is exactly what we need to do in the subproblem 1, right? How do we see that this is true? Well, our E in is minus log of our estimated probability given the Gaussian model, the mixed Gaussian model of seeing these D points, right? The only difference is now in this step we are given this B. Yeah, so we are given the set of points in the bumps. Yeah. So what is this equal to? Yeah, this is the probability, joint probability of seeing all of these data points, right? But these data points, they're generated independently. So we can just multiply the probability of generating each point. Yeah? So this minus log of product, n goes from 1 to n, p of generating this point, again, given bj. Right? Yeah? Okay. And so this big product over all of the points, I'm going to do one more step. I'm going to group them into different bumps. Yeah. So I first go on the bump j to k, and then within each bump, I'm going to do xn in bj. Yeah. In here, I don't have to write bj anymore because now within the j's bump, I just write given j's bump. Yeah. It's independent of other bumps, right? Yeah. Okay. So within the j's bump. And if you want, you can, this log of the product can be written as sum of the logs, yeah? So j equal to 1 to k, sum xn is in bj, this p xn given j, yeah? Right? Everyone's, so far so good, right? No, not too hard to get to this point, yeah? Right. Now, what is this one? Well, we don't know, right? This one is simply our bump, that PDF of the bump, right? This is just a normal PDF. Yeah? So this is just n of xn, and then mu j, sigma j, yeah? And this is equal to, we have a formula for it from before, yeah? This d over 2, and then the determinant, square root e minus half minus mu j. It's a pretty symmetrical form. Mu j, just like that, right? Just the d-dimensional Gaussian PDF. Yeah, that's what this p hat of xn given j is. Right? Given this j is a Gaussian shape, as we hypothesize. So therefore, for each j, we just need to minimize the above, minimize this sum, minimize over mu j, sigma j, this sum above, right? Yeah, just the sum above. Turns out that this is a classical estimation problem. Yeah, basically given the data points that you have generated from a Gaussian PDF, how do you estimate the mean value and the covariance? Yeah, so that's exactly what we have. What you do to minimize this, we just simply take the gradient and set it to 0. Yeah?
Just the sigma in the equation for the distribution, just a little bit. That
Oh, sigma j. Yeah, thank you. Yeah. Sigma j. Thank you. J here. J. Yeah. And to minimize this, this turns out to be again a convex problem. You set this and the gradient with respect to the sigma j, to 0. Now, this one is pretty tedious to calculate this gradient, but it can be done. And if you go online, you can find the gradient of the Gaussian sums, with respect to this covariance and so on. And then if you set them to 0, you will see that indeed we get the solution that as we have, the intuitive solution. The mean value is simply the sample mean. The covariance is simply the sample covariance. Those turns out to be optimal. Okay, they're optimal estimators to maximize this probability, this conditional probability given the BJ, the probability of seeing the data points that we are given. And that's exactly what we want. We want to find the best fit parameter based on the data point that we have. Okay. So therefore, even though you only need to remember that for our algorithm, these are the only things you remember on top, right? That's the only thing that we need to do, but these are well-justified procedures. So that's subproblem 1. And then subproblem 2, of course, now we're given the omegas, the parameters for the bumps, the Gaussian parameters, and the probability of choosing the bump, j equals 1 to k. We want to estimate the membership again. Bump membership. How do we cluster those points, given that each cluster has those parameters? So, in other words, for each point, xn, we want to find the best bump j, that is the most likely to generate this xn. To produce, let's see, xn. In general, we'll pick these bumps at random to pick this to generate these data points, right? Which bump is the most likely that we have used to generate it? So mathematically, basically we're saying that J star, the optimal J, will be the argmax over all of the J's, all of the bumps. The probability of J given xn, right? That's what we want to maximize. But what is the probability of J given xn? Well, we know the other way around, right? We have the density of xn given J. So to flip this order, we use the Bayes rule, So simply B-A-Y-E-S apostrophe. Remember the apostrophe is at the end of Bayes, because the name contains the S at the end. Bayes rule says this is equal to this given J multiplying the probability of J, divided by P of xn, right? Now, what is P of xn given j? Well, we already have. That's just the bump density, right? The density of bump j. So xn mu j sigma j. What is pj? What is the probability j? Just wj, yeah? Wj, by definition. We all know that. And here, the bottom, the P of xn, we can use a total probability theorem just to, that's just a general base rule anyways, right? So all possible bumps, I goes from 1 to k, then we have P of xn given I times probability of I, yeah, which is just wi anyways, yeah? But turns out that we don't have to care about this denominator, because this denominator does not depend on j, right? It's just a simple P of xn, okay? It's independent of j. Independent of j, yeah? So therefore, no need to compute. Even though it looks a lot of work to compute, right? So therefore, to optimize, to maximize this ratio, we just need to maximize the numerator, yeah? So we just do argmax over j of the numerator. Let me put the wj in front, just looks nicer. Mu of j, sigma j, like that. Okay, and that's it. So that's what we need to do for the subproblem 2. Yeah, we have to just find the maximum of this form. And if we have a k reasonably small, we can just do exhaustive search, right? Just check all of them and pick the best one. Okay? Yeah. Yeah, it's just a normalizing constant anyways, right? It doesn't matter what it is. Yeah. So therefore, we can just write the EM algorithm just like that. Okay, nothing really is challenging here, right? Except that, well, we say this is a hard decision EM, okay, which implies that we're going to have a soft decision version of EM that we'll talk about right after this. Yeah, but let me write this out first. The input, of course, it will be the data that you have, and then a choice of k. Yeah. So we initialize. It's going to be alternating, right? So we have to initialize something. So some arbitrary membership, let's say, arbitrary bum membership for each xn. Let's say in D. Yeah. One very common example is, again, simply do k-means. No, again, this is the first time we see this actually. Yeah. Yeah. We just use k-means to group them by their Euclidean distance. Okay. Turns out to be a reasonably good initialization usually. And then you can, after you have this membership, the initial one, you can estimate the parameters, yeah, omega, right, given bj, right? Now we have decided the bj based on our k-means. Yeah. Of course, this will be subproblem 1. Yeah, we know how to solve it. Number 3, now once you have those parameters, now you can update. Update bump memberships. bj given omega. I mean, I'm writing this really just redundant, right? But anyway, just for completeness sake, let's write them down. This problem 2. And then you repeat until convergence. And 3 until convergence. the problem is that to show convergence, well, first of all, the convergence is guaranteed, okay? Just like k-means, convergence is guaranteed, except that the proof of convergence is quite a bit harder than k-means. Okay. But it has been proven. Convergence is guaranteed. The main reason is that this E in omega, unlike in the k-means case, we know the E in omega just keeps decreasing, yeah? And then there's a low bound, so you know that converges by the monotone convergence theorem, okay? We don't have that in EM, okay? What we have, what we optimize, remember, in this part, we say we optimize this E in only given Bj like that, okay? Turns out that to show convergence, you cannot use E in omega alone. We have to use another so-called potential function to show that that potential function keeps decreasing. But you know, it's out of the scope of this course, so we're not going to bother with that. Yeah.
Is the potential function somehow transformed?
Yeah. It is one way to use the one potential function would be the likelihood of seeing this theta d, and also the bump membership Bj as well at the same time, joint probability. Okay. One way, but there are different ways. And in fact, another way to prove this convergence guarantee is just to say that, well, EM algorithm in general converges. Yeah? An EM algorithm, as we stated here, is only a special case applied to Gaussian mixture models. EM algorithm actually can be applied to more general forms. And in the appendix of the textbook, there's a proof of convergence for the EM algorithm in general, yeah? Not just for Gaussian. Okay? So you can just say, well, that one can be proven in that way. But if you want to have a shorter proof, because the one in appendix in textbook is very messy. You can take a look. It's really, really hard to read. Yeah. But for the Gaussian case, there's an easy way to do it by using that potential function that I mentioned. But again, it's outside of the scope of this work, this course, so just know that it converges. That's good enough for us. Another thing is that this Bj, this membership, this set of parameters, they are auxiliary variables, right? Or sometimes called hidden variables. Yeah, because at the end, the Gaussian mixture model does not require this Bj, right? The Gaussian mixture model only requires the big omega. So we just use, in a way, we use this Bj to help us to iterate until we get the Gaussian mixture model. Yeah? So you can throw it away at the end if you want. Yeah? So it can be thrown away at the end. Okay. So that's the hard decision EM. Okay. Now, of course, then we have a soft decision. Yeah. In the hard decision, what we are saying is that in subproblem 2, we force a decision to say that every data point we're going to allocate it to a bump. Okay? But you notice that in the Gaussian mixture model, this Gaussian distribution, the Gaussian distribution goes to infinity, minus infinity, right? Has infinite range of support for the for Gaussian distribution. So it can go anywhere, those points. There is no hard boundaries like in k-means, right? For each bump, it's possible, even though with a pretty small probability, that that point can be very far away from the mean value of the bump, right? Unlike in k-means you have hard boundaries, okay? So therefore, that gives you a sense that, well, maybe we don't have to assign the hard decision on each point, yeah? So that's how we get this idea of a soft decision for EM. Soft decision in EM. So we assume that each point can be divided into different pieces. Each piece is put into one bump. Okay? Each point will be cut into k different pieces. Now, how much you cut, which piece is bigger than the other? Well, that's something that you have to calculate. That's all. Okay? So we assume each data point is divisible So we're going to define this new variable, gamma nj, as the portion of the nth point that we put into the bump j. Yeah? So the fraction, or more mathematically, you can think about it as the probability, another way to look at it, of xn, the fraction belonging to bj. Okay? You go into kind of a quantum physics type of argument about what we mean by probability and so on. Yeah, whether the cat is alive or dead or alive and dead at the same time. This is a fraction of whether it belongs to this case or belongs to that case. And of course now, because it's a fraction, it has to be greater than or equal to 0 and has to sum to 1. Yeah, j equal to 1 to k. This fraction nj is equal to 1. Right? Yeah. So now we have to decide what are the proportions that we want to allocate to different bumps. So our subproblem 1 is, again, we want to estimate omega given this soft membership now. Yeah, this is not hard membership, but soft membership. Yeah. Again, we have to define this mj. Yeah, because we want to estimate wj and so on, right? What would be a good way to estimate mj? How many points are there in the bump j right now? If you divide, you chop up each point and spread them around, right? How do we count the number of points inside bump j? Well, just add up the fractions, right? Add up the fractions of all points. So now the summation will be, there's a sum of n goes to 1 to n, the fraction of each one of these points, right? So mj will be the effective number of points in bump j, yeah? But if you think about in terms of probability sense, then this would be expected number of points. In the bump j, in bj, yeah? Okay. Once you have that, then we say, well, wj, again, can be estimated by nj over n, right? Same as before. How about mu j? Mu j now is the average of those points, but only partially, right? So now we have to say there are, well, on the expectation there are so many points, but what are the values? The sum value, we have to sum up all points, right? Because every single point has the probability to be inside, has some part of that point inside this bump j, yeah? So how many is the portion? Well, gamma nj, right? That portion of xn is in bump j. So this is the amount of xn that's in bump j. We have to add up all of them, or add up this value over all data points, right? Now we have to have the expected value inside this bump, right? It's still easy to understand, right? Pretty straightforward. And likewise, the covariance is the same. Now, instead of just summing up, a hard decision, those points, now it's a soft decision. You have to sum up all of them, a portion of that, gamma nj portion. And then the rest is the same. And xn minus mu j transpose. Oops, no, just xn minus mu j transpose. Second one, like that. Okay, again, the only thing difference is that now every single point can be inside that bump. Yeah, it's only with a portion. So that's all. That's all that we change, right? Nothing else. So we're done with subproblem 1. How about subproblem 2? Well, of course, now we have to update the soft membership, which is gamma nj, how we cut these points, yeah, given the parameters of those bumps. Right? So how do we calculate this? Just simply saying that this is the probability, right? The likelihood that that point will be in this bump, pretty much. Yeah, the portion of the bump, fraction of the bump, fraction of the point that's inside the bump. Previously, what did we do in subproblem 2? Previously, when we have to make a hard decision, we just say this one, right? previously we do this. Yeah, we forced to make a decision, right? We pick the best J out of that probability. So right now we're saying that we don't have to force ourselves. We don't have to make a hard decision. We just keep this probability. That's good enough, right? That's the probability that this point is inside the J. And we just interpret that probability as the fraction of the point that's inside the bump J. Yeah? So therefore, gamma mj, we simply set it to just the probability of bump J given xn, right? What is the probability that xn is in bump J? Make sense? Yeah? So in fact, the soft decision version of En is actually easier to compute than the hard decision, right? We don't have to do that outmax, the maximization anymore. We just set whatever probability it is. Yeah? This point can be in every bump, yeah, just with a different probability. We don't have to force to pick the maximum probability. And of course, from the previous case, you already have the formula, right? It's simply Wj n of xn mu j sigma j, and then this summation I over 1 to k wi xn, oops, is it mu I sigma I, yeah? Just the base rule again, right? Okay, and then we're done. This is the subproblem 2, as simple as that. Okay, so if you write this up, the so-called soft EM. In fact, this one is easier to compute, so that's why the textbook does not even introduce the hard EM. The textbook just directly jumps to the soft EM. Yeah. But in most other places, you see the hard EM. Yeah. So I think it's easier to understand the hard EM first, even though computationally, soft EM is actually faster. Especially since we learned k-means, right? Hard EM is connected with k-means better. Yeah. So again, we initialize arbitrary gamma mj. Yeah, of course, for n is in between 1 and n, and then j is between 1 and k, right? For all bumps and all points, we initialize this. And one common thing you do is just use k-means again. Yeah? We can use k-means because, this probably can be just 0, 1, right? Yeah? As the initial point, nothing wrong with that. We say the probability is just 1 is in that bump and probably 0 in none of the other bumps. This is one valid solution. Yeah? Therefore, it can be a valid initial point. So we can use k-means again. We don't have to do anything different. And then the rest is the same, simple. Yeah? Now you're given mj. Yeah? You estimate omega, and then given omega, you estimate, or you update if you want, doesn't matter, mj, the gamma mj, yeah, and then repeat until convergence. So it turns out the soft EM is nothing, special really, right? Nothing challenging to understand. Yeah. And for the hard EM itself, it's very similar to k-means. The proof of optimality takes a bit of time, yeah. But you can ignore that if you don't, you're not comfortable with that part. Yeah. So overall, I hope today's lecture is not that heavy, right? It's a bit. Everyone is stressed out, so hopefully we're doing okay so far. Yeah, no, I know it's a bit tight. Yeah, I apologize because the midterm we have to do it on tomorrow for most of you. Because I was hoping previously, the midterm will be on Thursday, right? The regular midterm, most of you will be on Thursday, but we cannot find a room, so we ended up on tomorrow so soon. Any questions about anything, about the midterm, anything? Any questions?